hello, off we go. We're going to do some examples on example questions on limiting and excess reactants. We are going to use this page 57. We're doing some serious jumping around in your packet of things. If you've got your packet and you notice that we have just like blindly skipped past this, this is a great tool, and totally feel free to use it to like understand the concept a little bit better. It's a little tricky because it's not the easiest thing to write on a piece of notebook paper. And so for here, even though it is wonderful and we would usually do it, the other thing about these is these are better in groups. Awesome. So since we have no printers and no groups, zoop. Womp womp. You may also notice that we have blindly skipped past a lab. That is what I like randomly remembered in the middle of the other video. We're gonna do the lab tomorrow, and since you probably can't do this in your own home, I will link a video to you and possibly a couple videos. It's a cool lab. It's the kind of lab that if we could get together for like a small handful of labs, that would be a nice one to see, just because you form some products that like are kind of cool. So I'll try to get you a cool video on that, and we'll do that tomorrow. And we're actually going to use the lab as a review tomorrow, on Thursday. Totally getting ahead of myself. Let's do more math. This is exactly what you wanted on your morning, right? What could be better than like more calculations? Part 2, go find your calculator. Where's calculator? There's calculator. Okay. Yeah. So we just figured out limiting and excess reactants. And where am I going? Oh, right. And you know that the math is actually going to look very similar to what you already know. And because it's very similar to what you already know, I'm not going to do a huge amount of talking through, although I'm realizing this first one throws a slight wrench into your works. How many moles of NH3 can be produced from the reaction of 28 grams of N2? Also realized they did not balance that reaction for you. That's a bunch of bogus. This page is an interesting page. Let's balance that reaction, and by balance that reaction, I mean I'm going to tell you the coefficients, because that'll help. And in fact, anytime you're working with reaction, you need it to be balanced. Can't hurt to check. You could do that on your own. You can balance that. You can even like cover this up and practice it, but kind of wish it had printed balanced. That'd be nice. Here's the other wrench in your works. The unit you are solving for here is that unit. Doom, doom, doom. Okay, equals sign moles of NH3. That's not so bad. You actually solve for moles of your product inside of that 4-step stoichiometry thing every single time. Let's see if we can figure out where in that equation you're solving for moles. Okay, this part looks predictable though. Can be produced from the reaction of 28 grams of N2. That's your starting thing. Let's just do some typical stoichiometry, although we are going to note that what we want left on top is moles of NH3. We know we're changing compounds, so we know that we need to get our starting compound into moles so that we can do our mole ratio. And we know we need a mole ratio comparing moles of whatever we're starting with to moles of whatever we're ending with. Since we're not solving for grams, you don't need that second molar mass. You just solved yourself for moles. So this particular question asked you for moles. And you can solve, you solve for moles every single time. It's possible you didn't realize you were doing it, but in the middle of that stoichiometry, you can just chop off that last moles to grams step, solve for moles. That's a thing you can do. Aside from that, it's going to look real similar. Here's your molar mass step. You're comparing grams of N2 to moles of N2. A single N is 14.01. If you've got two of them, a molar mass of N2 right there. It's that many grams in 1 mole of N2. Here's your mole ratio. Pull your coefficients from your balanced chemical reaction now that it's actually balanced. That's helpful. Moles of N2 has coefficient of 1. Moles of NH3 has coefficient of 2. Did I edit this page? Because this is going to come out real close to 2, because I'm doing 28 divided by 28 times 2. So, like, maybe that's 1.99, but, like, that's probably just 2. I don't know if I even have to math that, but let's do it. 28.02. Yeah, great. Okay, 1.99857. And we're looking for 2 sig figs anyways. Okay. This will still tell you or show you the concept, even though, whatever. Moving on. Okay. How many moles of NH3? So you'll notice that we're solving for the same product here, and we're even solving for the same unit of that product. So we want moles, and that's really handy because once we have these two numbers, now we can compare them because they're both moles of NH3. You can choose any product that you want to solve for. Here you only have one product, so let's solve for that one. Once we have those numbers, we can compare. All right, here we're starting with 28 grams of N2. Here we are starting from can be produced from the reaction of 25 grams of H2. So you might initially look at this and say 28 is bigger than 25, duh. But you're gonna do your math because the molar, well, because you don't know what you're gonna find. Let's just summarize it that way. You still want moles of your product on top, and you're going to convert your grams to moles of your starting thing and then compare mole to mole. There's your mole ratio, there's your reaction step. 1 mole of H is 1.01, so 2 is H2. We've got 2.02 grams of H2 for every 1 mole. So hydrogen just weighs less, which makes sense. You can make a blimp out of hydrogen. It is not recommended, but you can. Interesting. Okay, let's do your mole ratio step. Just pull your coefficients. NH3 has a coefficient of 2. H2 has a coefficient of 3. Okay, so that's gonna like throw some wrenches in your work, maybe a little bit. And that's gonna be about 8, right? 2 over 2. 25 over 3. Get the calculator out. I'm multiplying across the top, so I'm doing 25 times 2, and then dividing all the stuff on the bottom, divided by 2.02, divided by 3, about 8. That answer makes sense. So the calculator says this, and we want 2 sig figs. Okay, that 5's going to round up. Alright, so even though we started with more grams of N2, since N2 weighs so much more than H2, once we crunch this out, 28 grams of N2 can form 2 moles of NH3, whereas 25 grams of H2 can form, 8.3 moles of NH3, of that same product. Okay, so what we just did kind of normal stoichiometry. They threw a little wrench in your works with asking you to solve for moles instead of grams, but got there. It's not so bad. In fact, it's even easier. We could put these moles of NH3 back into grams of NH3. That would be totally fine. Just get the molar mass of NH3. But what you're actually starting to see here is that since these results are comparing the same product and the same unit, moles of NH3 and moles of NH3, we can see which reactant ran out first and which was extra, which we had too much of. So your limiting reactant runs out first, causes the reaction to stop. When you calculate it, it calculates to the smaller amount of product, whereas your excess reactant, there's extra left over. When you solve it out, that solves for the larger amount of product. Just did a whole bunch of math, compared the same product, same unit, same product. The smaller amount of product shows you the limiting reactant. Okay, so down here where it says which is the limiting reactant, we can say the limiting reactant is, find your smaller amount of product, that points directly to your limiting reactant. So your limiting reactant is 28 grams of N2 because it can only form 2 moles of NH3. That's the most it could form because it can only form 2 moles of NH3. And the question doesn't ask it, but we can do it anyways. If N2 is the limiting reactant, we can write a sentence for the excess reactant also. So the excess reactant whichever one could make more product, that's the one you have extra of. There's excess, there's more than you need, there's too much. There's excess of, excess of H2. So the excess reactant is at 25 grams of H2 because it could form a whole 8.3 moles of NH3. There's extra of that H2. Does that kind of make sense? The N2 is forming a smaller amount, so it's the limiting thing, the thing that runs out. Whereas the H2 could form a bigger amount, there's excess. All right. Excellent. Well, what do I want you to do next? I want you to do some practice. I'm realizing that this is not remotely balanced. I'm also realizing that I printed you the same thing on both sides, which is like not very helpful. So I want to edit this. Hold your horses, or hang out and watch the balancing of a combustion reaction. Great, I'm just going to do this over here. Starting with some C, some H, some O. Turns out atoms can't be created or destroyed. This is completely unnecessary, except that this worksheet is not sufficient yet in its current state. So I'm editing it in front of you. Let's hope I can get this some consistency. Okay, so I know that I need 3 carbons because I start with 3 carbons. That's going to give me 3 times 2 is 6 oxygens. Here's another hint if you're balancing combustion. All of your other groups of oxygen come in little groups of 2, so this H2O is the anomaly. You're always going to have some sort of even coefficient if you have a odd number of O2s. Combustions are the hardest to balance. So I'm going to guess a 2. You may find out in real time. I could be totally wrong. And I'm wrong. Okay, so I have 8 hydrogen over here. So I need to use up 8 hydrogen over here. Let's put 4 right there and see if that works. So now we've got 4. 2 times 4 is 8. Yay! Now my carbons and my hydrogen's balanced. And that's how to, I mean, I might still be wrong, but when you're doing combustion, do your carbons and your hydrogens first, because your oxygen is just all over the place, so like don't even mess with it yet. You now have 4 times 1 oxygens plus 3 times 2 times 3. Let's do that math right. So 4 plus 6 is 10. Oxygens, red. And over here you're going to get some weird odd number. Do a little check. 3 carbons, 8 hydrogens, 8 hydrogens. 4 plus 6 oxygens is 10. 10, okay. Cool. As always, bonus points if you find me making mistakes. Especially if you share it with class and therefore everyone can learn. But let's give you those coefficients so that you don't have to do that. And go ahead and try this one. And let's make sure the question makes sense. Moles of water, you can do that. Produced from that much of this. This looks fine. Alright, try this on your own. If you super want more practice, you're welcome to try this one also. You're welcome to try anything on the back that you know how to solve. So you're going to run into some words. Here's a word that you don't know what it means. When you run into a word that you don't know what it means, don't worry about it. We'll get that tomorrow. This is a word you can solve for right now. You could solve that. Oh, here's another word. Don't know this one yet. Let's do that one tomorrow. But definitely, so everybody is going to do this weird combustion question. If you want more practice and you want to see it another time, try it out with these questions over here, but don't worry yourself about the words that you don't know, because I will teach you those tomorrow. All right, enjoy.